Isaac Newton established physics as the key to understanding the universe. His laws became the ultimate universal truth. But by the late 19th century, classical physics was crumbling. Newton's laws struggled to explain the mysteries of light and matter at high speeds. From the Netherlands rose a young mind, Hendrik Lorentz. He offered answers that reshaped science itself. His ideas were so profound that Einstein built his theory of special relativity upon Lorentz's foundation. In 1902, Lorentz was awarded the Nobel Prize in Physics for his groundbreaking work. This is the story of the genius who became a bridge between Newton and Einstein.
Born in Arnhem, Netherlands in 1853, Lorentz showed prodigious talent from an early age. By 16, he was studying advanced mathematics that left his teachers in awe. At just 19, he published his first scientific paper on the theory of reflection and refraction of light. 3 years later, in 1875, Lorentz completed a groundbreaking doctoral thesis, expanding that work with Maxwell's equations. It was so advanced that it drew the attention of leading scientists across Europe. In 1878, at only 24, Lorentz was appointed professor of theoretical physics at Leiden University, a position he would hold for the next 45 years. Hendrik Lorentz proposed that all matter is made up of tiny charged particles, which he called electrons before they were experimentally discovered by J.J. Thomson. These electrons are tiny, negatively charged particles. Unlike solid spheres imagined in earlier atomic models, they are point-like and mobile, capable of moving and responding to forces. These electrons are not passive. They oscillate, move, and interact, giving rise to electricity, magnetism, and the optical behavior of materials. Matter was no longer a dead material as previously thought. It was dynamic, alive with motion at the microscopic level. Lorentz formulated the precise rules governing how electrons move. He introduced what we now call the Lorentz force law.
One of Lorentz's most remarkable insights was the connection between electrons and light. He proposed that light interacts with electrons bound in atoms, causing them to oscillate. These oscillations explained optical phenomena such as reflection, refraction, and dispersion. Remarkably, Lorentz developed this theory before electrons were observed experimentally. They were discovered in 1897 by J.J. Thomson. In 1895, Hendrik Lorentz introduced a set of mathematical equations to describe how space and time coordinates transform for objects moving at high speeds, close to the speed of light. Classical physics assumed that time and distance were absolute, but Lorentz realized that light always travels at the same speed no matter the motion of the observer. To reconcile this, he formulated transformations showing how length contracts and time dilates for fast-moving objects. These effects are now commonly referred to as length contraction, time dilation, and the relativity of simultaneity. Lorentz's equations provided the mathematical framework that Einstein later used in his special theory of relativity, 1905. In everyday terms, Lorentz transformations explain why GPS satellites must account for both motion and gravity, and why particles and accelerators behave differently than Newtonian physics would predict. In short, Lorentz showed that space and time are not absolute, but relative, and that the universe follows deeper rules than classical intuition could imagine. In 1896, Peter Zeeman discovered that when light from a glowing gas is subjected to a magnetic field, its spectral lines split into multiple closely spaced lines, a phenomenon later called the Zeeman effect. classical physics could not explain why a single wavelength would divide under a magnetic influence. Hendrik Lorentz provided the explanation using his electron theory, which proposed that atoms contain tiny, negatively charged electrons. According to Lorentz, electrons inside atoms behave like tiny oscillators. When a magnetic field is applied, it exerts a Lorentz force on these electrons, slightly altering their motion. This change affects the energy of the light they emit, causing the observed splitting of spectral lines. The Zeeman effect became one of the first experimental confirmations of the electron theory, demonstrating that electrons are real, measurable particles whose motion governs the behavior of light. This discovery not only validated Lorentz's theoretical framework, but also paved the way for future developments in quantum mechanics and our understanding of atomic structure. Hendrik Lorentz extended his genius beyond electrons, exploring the connections between hydrodynamics and electrodynamics. He recognized that the mathematical methods used to describe the flow of fluids could also be applied to electric and magnetic fields, revealing surprising analogies between seemingly different phenomena. In hydrodynamics, particles move through a medium under forces like pressure and viscosity. Lorentz realized that charged particles in electromagnetic fields behave similarly, responding to forces in predictable ways, just as fluids follow the equations of motion. By applying this framework, he could describe the behavior of electrons and electromagnetic waves with greater precision, unifying mechanics and electromagnetism. This work not only strengthened his electron theory, but also provided a deeper understanding of light propagation, wave interactions, and energy transfer.
Lorentz's brilliance earned him the Nobel Prize in Physics, which he shared with Peter Zeeman in 1902, recognizing their work on the influence of magnetism on radiation phenomena. He was also made a Fellow of the Royal Society in 1905. In 1925, the Royal Netherlands Academy of Arts and Sciences established the Lorentz Medal to honor and celebrate outstanding achievements in science. Even the Moon bears his mark with crater Lorentz, a large lunar crater named in his honor, standing as a testament to a mind that forever transformed our understanding of the universe.
Hendrik Lorentz passed away on February 4, 1928, leaving a legacy that reshaped modern physics. To young scientists, he was a mentor, a guide, a fatherly figure. His work laid the foundation for Einstein's theory of special relativity and opened the door to the subatomic world with his electron theory and explanation of the Zeeman effect. He sparked a revolution in physics, inspiring pioneers like Niels Bohr and Max Planck to explore the strange, unseen realms of quantum theory. As chairman of the first Solvay conferences, Lorentz bridged the world's greatest minds, mediating debates between relativity and quantum mechanics with wisdom and grace. But Lorentz was more than a scientist. He was a peacemaker, helping rebuild European scientific cooperation after World War I and contributing to the League of Nations Scientific Committee. Hendrik Lorentz, mentor, visionary, bridge between worlds, forever changed how we understand the universe. This is Awards, where we celebrate the people whose ideas changed the world. Don't just watch history, be inspired by it.
Thanks for being with Awards. Subscribe to know more about international award winners and unsung heroes behind peace, science, and humanity.